Hey 13 diplomas and welcome back to topic 7 recap. This is part C. So we're just going to launch straight into it. We are partway through Le Chatelier's principle and we just talked about concentration changes. So the second change that can be made to a system at equilibrium is a pressure change. Now, this will only affect systems where your reactants or products are in the gas phase, and that's really important. And when you justify your answers, you must actually specify gas moles or gas particles, or else you won't get full marks. So let's just talk about what exactly is pressure. So pressure is gas particles colliding with the walls of a container, and they exert a force, and this force is pressure. So the way to change pressure is actually by changing the volume. So if you look at these two situations here, same amount of particles in each of these vessels, except this vessel has a much larger volume, and because it's got a much larger volume, it'll have a lower pressure, whereas though this system here has got a much smaller volume and therefore a much greater pressure. Okay, now again, just like concentration, this will not affect Kc because the changes are relative. If the concentration of product goes up, the concentration of the reactant goes down, and so it always evens out. Okay, so how can we increase the pressure? Well, we just mentioned one way, reducing the volume, okay, of a closed system. The other way is that you could add more particles, okay? So you could add more particles or you could reduce the volume. And let's talk about what happens. Remember with Le Chatelier's principle, I'm trying to get you to get into a routine of always stating the direct opposite first. So if the pressure of a system is increased, then the equilibrium will shift to decrease the pressure. Okay, now the only way to decrease the pressure in an equilibrium system, because you can't alter the volume, the only way to do that is to shift to the side with the least gas moles. Okay, because the less particles means a lower pressure, and that'll readjust the system. So then the opposite would happen if you decrease the pressure. So if the pressure was decreased, the equilibrium would shift to do the direct opposite and try and increase the pressure, and it would do that by moving to the side with the most gas moles. And that's because the two ways of altering pressure, as I've stated before, is by changing the number of particles or changing the volume. Okay, so those are your kind of answers, and those are your two rote learnt answers. There's no trick to it. If you can understand that and regurgitate that, you'll get full marks for the pressure question. Now, you must use gas moles. You can't just say moles because these systems only relate to gas. Okay, so it's really important. So here's a really common question here. So you've got NO2 and N2O4. So let's say that the pressure of the system is increased. So if the pressure of the system is increased, then the equilibrium is going to shift to decrease the pressure. Now it'll do this by moving to the side with the least gas moles. Okay, and in this case, you've got your reactant side having 2 and your products having 1. So the reactants have 2, products have 1, so therefore equilibrium will shift to the right towards the products. So hopefully that makes sense, and you can see I've answered this here. So if a pressure is increased, the system will act to oppose this by reducing the pressure by moving the side with the least gas particles. Okay, reactants have 2 gas moles, products have 1, so the equilibrium will favour the forward reaction. Okay, and because these two have colours, you could get asked what would happen to the colour of this equilibrium. Well, because you're making more colourless solution, colourless product, the solution would become less brown. I hope that makes sense. So here's another example. This one's really common. So let's say that we decrease the pressure. We know that the equilibrium will shift immediately to do the opposite, to increase the pressure, and it'll do this by favouring the side with the most gas moles. Okay, the most gas moles. Now, 1 gas mole here plus 3 gas moles makes 4 moles of gas on the reactant side to 2 moles of gas on the product side. So therefore the equilibrium is going to shift to the left or the reactants. It doesn't matter what one you say there. So let's just have a look at my model answer. As the pressure is decreased, the system will act to oppose this by increasing the pressure. It'll do this by going to the side with the most gas moles. Reactants have 4 moles, products only have 2 moles, therefore the equilibrium shifts to the left. Hopefully that makes sense. Here's one more example, and this one's quite important. What happens if there's the same numbers of gas moles on each side? I love asking this question. It usually comes up as a multi-choice, and the answer is absolutely nothing because they're the same. So if you alter the pressure of this system, it does nothing because you've got 2 to 2. So equilibrium can't do anything to relieve that. It just stays status quo. Okay, we're now on to change 3, temperature change. Really, really, really important. Temperature will change the equilibrium constant, okay? Temperature will change the equilibrium constant. It actually completely favors one side over the other, so it's not like your concentration and your pressure changes where if one thing goes up, one thing goes down, and therefore in your mathematical calculation that comes out as the same figure. This does not, okay? However, these questions here are quite easy to understand because the same thing happens each time. So we know that if we're talking about a temperature change, the type of reactions that, or the systems that can respond to this are exothermic, endothermic reactions. And we remember exothermic is a reaction that releases heat energy. So exo releases heat energy and endo absorbs. And that's always the case, okay? And we're going to use the principle of that to be able to work out what's going to happen to our equilibrium every time. So if there's a decrease in temperature to our equilibrium system, we know Le Chatelier's principle tells us that it'll do the direct opposite. So equilibrium is going to shift to increase the temperature. Now, how's it going to do that? Well, the only way to increase the temperature of a system would be to favor the side of the reaction that releases heat energy. Because we know that a reaction that's exothermic in one direction is always endothermic in the other. And so therefore, every time temperature is decreased, the equilibrium will always try and increase it. And it'll do that by favoring the exothermic direction because that releases heat energy. So that happens every time. So that sequence of 3 never ever changes. And that means that the opposite's going to happen if we increase the temperature. So if we increase the temperature, the equilibrium is going to shift to decrease the temperature to minimize that change. And therefore it'll shift in the endothermic direction, which will absorb the added heat energy. And so it's really that simple. It follows this sequence of 3 steps every time for all of your temperature changes. So if we just have a look here, here's a reaction. Now what this is saying, just as a recap, we've got a negative sign here, which means that the reaction is exothermic, and it means that the forwards reaction is exothermic. So N2NO2 forming N2O4 is exothermic, and so that's exo, and that means that N2O4 breaking up and forming 2 NO2s is endo. And so you have to make sure you can understand that whatever the enthalpy written in the reaction, that's for the forward direction. Okay, so using the same example, so we know that the forward direction is exo and the reverse is endo. So let's say that the temperature is increased. If the temperature is increased, the equilibrium is going to shift to decrease that temperature. And how will it decrease the temperature? By moving in the endothermic direction, which will absorb the added heat energy. You must make a link between, once you've said endo and exo, you must say absorb or release, because that gets you the full 2 marks in diploma. So if we increase the temperature, the equilibrium is going to shift to decrease it, so it's going to move in the endothermic direction. As this is exo in the forwards direction, that means it's going to favour the left or reverse, which is endo. Okay, I hope that makes sense, and I've just spelt that out in a paragraph there. And if we were referring to colour, you'll remember that this is brown and this is colourless, so you're going to make more brown, which means that the solution would become more dark brown if they asked that. Okay, now let's do it again. It's the same reaction. Let's say this time that the temperature's decreased. If the temperature is decreased, the equilibrium is going to shift to increase the temperature. To do this, it's going to shift in the exothermic direction, which will release heat energy. In this case, the exo is the forwards direction, and you've answered the question. Remember, this is colourless and this is dark brown, so that means that more of the colourless means the solution will become lighter. It's still equilibrium, so you will still have some brown, so it's not going to be completely colourless, it'll just be lighter. Okay, so what does this reaction tell us about rate? What does the equilibrium constant tell us about rate? And the answer is it doesn't. Okay, when you look at these reactions here, you can look at temperature and you can look at the Kc as to where it sits in terms of products and reactants, but it doesn't tell us anything about the rate of a reaction, and that's something that you've got to keep in mind. Okay, that's the issue with Kc, is we don't know anything about rates. So even though in theory this temperature would produce a very large Kc, which is a lot more products than reactants, it actually is too slow, and therefore if something's slow, you're not going to make money from it. So just bear in mind, we don't know anything about rate from a Kc. Okay, so here's just the final part of this lesson is just running through some really significant equilibrium reactions. You will know from previous topics that this is the reaction NO is produced in a car engine. Okay, and it's a poisonous toxic gas, and so we want to turn that into harmless products. Yeah, so that's one of these reactions here, and you'll see that this process is endothermic. Okay, and so in order to produce when this is made, so this is a toxic product made in the engine, just to make this make more sense, and this process is endothermic, we then do side reactions to this. So what we want to do is try and shift it so that you make less. Okay, so you make less product. And so if we lower the temperature, the reaction is going to shift to increase the temperature, right? And if it's shifting to increase the temperature, it's going to shift into the exothermic direction, which means it's going to shift to the left, and you make more of the harmless reactants. And so that's why a lot of money goes into making temperatures of engines far lower. Just a wee summary, only temperature is the thing that affects Kc, and that's because one is favoured completely over the other. Okay, and this is all to do with activation energies, which we'll deal with a bit later on. Final thing is a catalyst. Now, we already know this, but a catalyst is something that speeds up a reaction by lowering the activation energy by providing an alternative pathway. It's that rote learnt sentence that you have to regurgitate. Because it lowers the activation energy, so you can see here this is with a catalyst and without a catalyst, it actually has no change to the reactants or products. They stay as they are, and therefore there's no change to the Kc. So the only thing that a catalyst does is increase the rate, which is beneficial purely on an economic basis if you're making something. So here's a wee summary of what happens to the value of Kc and your changes to equilibrium. So concentration, pressure, and temperature will all change your equilibrium position. A catalyst won't. And then the first two, concentration and pressure, will not change Kc, but your temperature will, and that's really important, and then that won't. Okay, so we're going to pause there. I have chucked heaps more of these graphs up onto your OneNote, which I think would be beneficial to you for you to have a look through, and I'm flicking through them now, and there's a few tasks with some answers that I've put in for you, which would also be beneficial to make sure you can do. We will be going through these in class, in a question in class on Teams shortly, but that is the end of your summary video on topic 7.